Suppose that we have 10 students and they're all competing in this contest. If we record the first, the second, and the third place, how many different outcomes are possible? That is not a difficult question, because imagine that we are rigging the game and we're selecting who's going to be first, second, and third. Then how many choices do we have for the first student? Well, 10. Now, how many choices do we have for the second place? Well, it is not possible for someone to win first and second place at the same time, so we are down to 9 students to choose from. And for the third place, we're going to have 8 choices. So altogether, there are 720 different outcomes. Okay, so suppose we have this contest, and now the first and second and third place gets to travel to where the finalists are competing against each other. And the question is, if the teacher has to buy the airplane tickets for the first, second, and third place, how many different outcomes are possible? Now, first of all, how is this a different question from the previous one? Suppose we number the students from 1 to 10. Suppose the first place was won by student number 7, the second place was won by student number 3, and the third place was won by student number 5. Then the same tickets are bought if the same 3 students came in but in a different order, right? In all 3 of these cases, while they are different outcomes, when we were worried about who's first, who's second, and who's third, when we just want to look at the 3 best students for buying the tickets, then these different outcomes need to be identified. And so the issue is here that order doesn't matter. So we start answering by saying, well, imagine that order mattered. Then the answer would be 10 times 9 times 8. But now we're in trouble because we have counted certain outcomes several times. For example, this one. How many times did we count 7, 3, 5? Well, if we get a little organized, which you know I like, let's say, so there is 3, 5, 7, 3, 7, 5, 5, 3, 7, 5, 7, 3, 7, 3, 5, 7, 5, 3. So these are 1, 2, 3, 4, 5, 6 different outcomes. So here is the bad news. If the question is how many different outcomes are possible for the ticket purchase, then 10 times 9 times 8 is too much, because we have counted certain triples several times. For example, our triple 357 was counted 6 times. Here is the good news. Every single number triple was counted exactly 6 times. So we get the right answer if we just adjust for the overcount by dividing by 6. Dividing by 6 would be the same thing as identifying these as one outcome. Okay, so let's see another example. Suppose we have 15 students, and now the first 4 we are interested in. And let's say the winning team means the 4 people who are going to travel for the finals. So if the order matters, turns out that's an easy question, right? The first place, there are 15 choices for the first place. There are 14 choices for the second, there are 13 choices for the third, and 12 choices for the fourth. So that's done. You should probably compute that. This is not too hard to punch in, but suppose the numbers are much bigger, say 150 and the first 10, that would be a little bit difficult. So there is a trick we can do. Let's make this a fraction first by dividing by 1. And now we're going to multiply upstairs and downstairs by the same quantity. And what we want, the goal here is that we could easily enter this into the calculator. So what we would multiply by is 11 times, 10 times, 9 times, all the way till 1. In other words, we would multiply both numerator and denominator by 11 factorial. Then the top would become a factorial, namely 15 factorial. And the denominator also a factorial. So this might be a little bit easier to enter into a calculator. Oftentimes, when the answer is this, you might see this. Books really like to present answers this way. But I like this one because this reflects the logic of it. So now for the trickier question is, okay, how many different ways can the winning team be formed? Which is the same as how many different ways can we select 4 items or 4 students out of 15, but the order they arrive in does not matter. When we have the same question, but the order doesn't matter, that's a harder question. It looks like for nature, order does matter. It is more natural to compute things where the order it does matter. So for the second question, the winning team, we're going to pretend first that order does matter. And then we're going to say, okay, but now surely we have overcount, right? Because if the 4 students that won, they are, say, students A, B, C, and D, then A, B, D, and C and A, B, C, D should be, they're different outcomes if the order matters, but not if the order does not matter, right? So the question here is, if we fully list this, how many would be on this list? And so the better question is, what kind of a list is this? So if we would list this, A, B, C, D, A, B, D, C, A, C, B, D, A, C, D, B, what are we counting here? What's that? Yes, you're right. We are counting exactly the following. In how many different orders can we arrange 4 items? Because that's how many different orders can the same quadruple come in. So this here would be a list, 4 times 3 times 2 times 1 long, or 24 long. And so the correct answer would be this divided by 24, because every single outcome like this was counted exactly 24 different times, because the same 4 items can come in 24 different ways. So we divide by 24, but just so you see the symmetry, we forgot to compute this. So what was this? So that's a lot of outcomes, 32,760. And this would be the same number divided by 24, which is 1365. Usually when we compute these numbers, usually there are easy cancellations, like 4 times 3 is 12, that can cancel out the 12, and then the 2 from 14. So then we just have 3 numbers to be multiplied, 15 times 7 times 13. So that's easier, 15 times 7 times 13. We got the same number. This is the answer if order matters, and we have to adjust for if order doesn't matter. So these have all kinds of names. Going back to the first example, when there were 10 students competing for the first, second, and third place, which we also didn't compute. What is this? This is 3, this is 4. We just cancelled out the 2 and the 3, so it's 120. This number is first of all called a combination, and the notation that mathematicians use is, it looks like a fraction but no fraction bar, and then there is this strange parenthesis looking like thing, and we read this as 10 choose 3. This represents the number of ways 3 can be selected out of 10, and that is the same as the number of 3-element subsets in a 10-element set. So that's a combination. In our second problem, when we had to choose 4 students out of 15, the first one doesn't have a notation as much as the second one. This would be 15 choose 4. Now the calculator has this, where this is the 15, this is the 4. I have not seen this outside of America. The universal mathematician's notation is really this. It's always good to remember the definition. The definition is the number of subsets, because, well, let's figure out the formula. So the formula would be, n choose k would be, so this is, we have n students and we need to select k students out of it for purchasing the ticket. For the first student, we have n choices. For the second, we have n minus 1 and then n minus 2, and now we have to stop. We have to stop after we have k many numbers multiplying each other. Now, we can think of this as n minus 0. To count out k, but we start at 0, that would be k minus 1. Indeed, n minus k would not be correct. This is 15 choose 4, right? 15 minus 4 is 11. That is the first number that's not here. We stop at 15 minus 4 plus 1, because you can think of this as 15 minus 0, 15 minus 1, 15 minus 2, 15 minus 3. It's either 1, 2, 3, 4 or 0, 1, 2, 3. And in this case, in this formula, it's 0, 0, 1, 2, and so on until we're subtracting k minus 1 from this. Now we have a tremendous overcount. This would be a good answer if the order mattered. If the order doesn't matter, we have to adjust for the overcount. And the question is, how many times did we count a single k tuple? It's called a k tuple. Well, the answer is, well, as many different ways it can come in. And that's k factorial. If the numbers are fairly small, this is the form that I recommend you use. But if the numbers are large enough, we can apply the same trick as we did here. So we can turn everything into a factorial if we just multiply upstairs and downstairs by a number that just picks up where this left off. So that would be n minus k minus 1, all the way down to 1. And now we have to multiply the denominator by the same thing as we multiplied the numerator by. And why did we do that? Because then the numerator is simply just n factorial. And then the denominator is just k factorial and n minus k factorial. So that's another form of the same formula. This reflects the logic to me, and this is easy to compute. So this is for ideas, this is for large numbers. When we compute combinations, it's always good to remember the definition. The definition is how many such element subsets are. If we ask questions like 10 choose 0, well, the formula does work, but for that we had to define, and these definitions were very natural in the sense that it worked just about every situation, is that 0 factorial is defined to be 1, and 1 factorial is also defined to be 1. So the formula would work, but there is no need to use that, because just remember the question is how many 0 element subsets in a 10 element set? And the answer is, well, just 1, the empty set. And even 10 choose 1. How many ways can we select 1 item out of 10? That's the same as the number of 1 element subsets in a 10 element set. And the answer is, well, that's 10. And then for the rest, the formula would work. 10 choose 2 would be, well, I have 10 options to choose the first one, 9 for the second one, and we counted everything twice, A, B, and B, A. So that's 90 over 2, that's 45. 10 choose 3, we have computed. 10 times 9 times 8. That would be a good answer if order mattered. Since order doesn't matter, we have to work for adjusting for that overcount, and that's 3 times 2 times 1. Basically, both numerator and denominator are a product, a permutation. The first one is starting with a full number, and we select the first, second, the third, and so on. And then the denominator is permutation that goes down all the way to 1, because the question is, these 3 items that we chose, how many different ways can we organize them? And that's, in this case, 3 times 2 times 1. So we did this, but never hurts. So that's 120. That's still not so bad to list. But I bet they get uncomfortably large to list as the numbers get larger. 10 choose 4 would be, we select first, second, third, and fourth, and then we have to adjust for the overcount, which is the answer to the question, how many different ways can we rearrange 4 objects? And that's 4 factorial. There are still nice cancellations. 4 times 2 is 8, boom, and then the 9 can become a 3, so that's 210. Combinations are also programmed into the calculators. So for 10 choose 4, again, we're going to enter things in the order we pronounce it. So we're going to say 10, and now we're going to have to find a choose 4. And these things will count in questions, come up in probability. So we go for the PRB button, and the first one is permutation, the second one is combination. We toggle under it and confirm our selection by pushing the equal sign or enter. 10 choose, and we're going to say 4. And then enter, there is 210. For a while, I'm going to ask that you know how to compute these combinations. We can use the calculator once we are just bored computing the same thing over and over, but I want you to know how to compute these things. What about 10 choose 5? So 10 choose 5, which is the number of 5 element subsets in a 10 element set, or the number of ways we can select 5 items out of 10. First, we pretend that order matters. And then we adjust for the overcount, which is the number of ways we can rearrange 5 items, which is 5 factorial. And then there is still nice cancellations. 5 times 2 is 10, 3 times 3 is 9, and 4 times 2 is 8. So we have 3 times 4 is 12, 12 times 42, which is 6 times 42. And we can check that using our calculator. So we're looking for 10 choose 5, 252. So our result is correct. Now for 10 choose 6. You know what? Let's go backwards. We're going to skip 10 choose 6, and we're going to come back. Now 10 choose 10, again, the formula would work, but who needs it? How many ways can we select 10 out of 10? And the answer is, well, just one way. Just one 10 element subset in a 10 element set. How many ways can we select 9 out of 10? Remember that we can say, if you need to select almost the entire set, why don't we just select stuff to kick out? So we can say that 10 choose 9 should be the same as 10 choose 1. That's that outer symmetry that we observed when we listed subsets. Well, let's see if the computation helps. So we're going to have 9 things upstairs and downstairs, and 9 factorial, and now there is a huge common factor, right? The whole, because this one doesn't do much, the whole 9 factorial can cancel out, and we got 10. But again, for 10 choose 9, I don't think we need the formula. We would just say that, yeah, that's 10 choose 1, and that's just 10. Now 10 choose 8. Our suspicion is that it's the same as 10 choose 2. Well, let's see. So we're going to have a product of 8 factors upstairs, 8 downstairs. Now, if we cancel out what we can, what we're left is 10 times 9 over 2, which is how we compute 10 choose 2. Let's see 10 choose 7. So I ran out of space there, so we're going to move here. So 10 choose 7, should that be the same as 10 choose 3? If we have to build a 7-element subset in a 10-element set, we can just select the 3 elements to kick out. So that would be, and now when we cancel out what is common, what we got, that is exactly how we compute 10 choose 3. So indeed, 10 choose 7 is the same as 10 choose 3. It was 120. 10 choose 2, I keep forgetting to compute these things. 10 choose 2 is 45, because it's 90 over 2. Now 10 choose 6 then should be the same thing as 10 choose 4. So we have already seen a combinatorial argument that n choose k, for n think 10, for k think 3. 10 choose 3 is the same thing as 10 choose 7. We already have the combinatorial argument, but we can just use factorials to prove that. This other form of combination, n choose k was n times n minus 1 times all the way till we have to have k numbers here, but we start from 0, so it's n minus k minus 1, or n minus k plus 1 divided by k factorial. And then we can turn the numerator into factorial if we just multiply by n minus k times n minus k minus 1, and so on, all the way down to 1, so that's n minus k factorial. And so then we get n factorial divided by k factorial times n minus k factorial. And in this form, it's almost trivially true that if you compute n choose k, that should be the same thing as n choose n minus k, because n minus k is k again. Let's look at 10 choose 3. It's 10 factorial divided by 3 factorial times 7 factorial. 10 choose 7 would be, well, now k is 7, so instead of 3 factorial, we have 7 factorial. But instead of 7 factorial, which is 10 minus 3, now we have 10 minus 7, which is 3 factorial. So it's from the formula, from the symmetry of the formula, it's almost trivially true that these two should be the same. Okay, before we go, let me ask you a question. And this is something that you're going to have to think about. I'm not telling you. What would we get if we added all this combination? And I'm not sure about the computational answer, but what I'm looking for, what is easier here, is a combinatorial argument why the result should be what it is. So think about that. Thank you for watching.